So this is the higher paper for 6.1, the distance time graphs, and first of all we've got an expanded formula sheet here. So we've got the multipliers and prefixes, and we've got a couple of extra equations in the mix. So question 1, let's go straight to the question. Describe how the acceleration changes during the 12 seconds shown. So you can see that it's a straight line from 0 to 2 seconds there, and then it starts to curve. So it starts to it's increasing at the decreasing rate there. So that's what I've said. The acceleration is constant for 2 seconds. Nice straight line, then increases at decreasing rate for a further 10 seconds. So from 2 to 12. And that's your 2 marks. By drawing a suitable tangent and using the formula acceleration equals gradient of the velocity time graph, calculate the acceleration when the car's at 5 seconds. Now what you don't want to be doing here is just drawing a line from 5 all the way up and then back and then put in 20 over 5, because that would be okay if it was a distance time graph, but this is an a velocity time graph, so this shows you acceleration. So what you want to be doing, a tangent, so draw that line, that green line up, little dot, get a ruler, and then you can see my gap this side is smaller than this gap this side, so really I should have been a little bit less steep on my tangent there, but I've used it anyway because they will give you a range for the marks to be correct within. So if it's at 5, I've gone either side. I've gone 4 and I've gone 6. I've gone an equal amount either side. I'll draw a line up, and I've brought it back, and then I'm going to be doing the difference in time. I'm going to be the difference in velocity there. So the equation that I'm going to use is A equals change in velocity over time. Well, change of velocity is V minus U. V meaning your final velocity, U meaning your initial velocity, or your starting velocity. So my time difference, but there is 6 minus 4, which is 2 seconds. My final velocity is 23, and we can have a look at that bit there. So you've got to just watch the scale because they go up in 0.5s. So it's 23, my final velocity, and my initial velocity is, the oranges for another question, is around about 15, 16, 17, 18 there, you can see. So when I plug that into the formula, the V minus U is 23 minus 18 over my time difference, which is 2, and that gives me 5 over 2, which is 2.5 meters per second. It wants the units as well, meters per second squared, because acceleration is meters per second, and that's why it's squared. And then use the equation from page 2 to estimate the distance. So if we look at page 2, there it is. And there is, it says, distance travelled, area under the velocity time graph. Well, we are dealing with a velocity time graph, so I'm going to use the area underneath. And the area is going to be half times base times height, because in this case I've got, it's more like a triangle. In the first 3 seconds, so that's the orange. I've brought it up, and even though it's a slight curve, it says estimate anyway. And I've brought that back to be 14 there, because it goes up in 0.5s. So it's going to be half this, because we only want this area. So half time base, which is 3 times height, which is 14. And that's where I get that calculation from, right there. And it comes out to be a distance of 21. Let me shrink that. And then another car of the same power and mass, but with a more streamlined shape. So that means it's going to get to its velocity quicker, because it's more streamlined, less air resistance. And it's a bit shocking, my graph here. You can see it's the main thing I need to do is to get, so in 2 seconds I need to get above what it was in my last graph, which was it was 14 meters per second, and then it needs to start curving. Well, if it's more streamlined, the acceleration is going to be steeper, and in the same amount of time, it's going to get to a greater speed. And that's what I've tried to do here. I've tried to show that in my 2 or 3 seconds, I've gone way above 14 meters per second, and then it starts to decrease. It starts increasing at the decreasing rate there. So it starts to tail off. You can't say tail off in an exam. You need to say increasing at the decreasing rate there, and it starts to come off. Okay, and then this one, an empty school bus takes 190 seconds. Okay, so I can always come back to the question if I need to. What is the question asking me? The bus accelerates uniformly from a set of traffic lights A. So there's A, the force acting on is 500 newtons. So we've got newtons, so I've already written down force, 500 newtons. Use the graph. The equations for page 2 to calculate the mass. So I know for 4 marks here, because it's 4 marks, I'm probably going to have to do 2 equations. And it also says equations there. So use the graph and equations from page 2. So it's asking me to calculate the mass. So there's no real formula that ties velocity, time, and mass up. But there is one that ties force, which they're giving me, mass, and acceleration. And I know if I got velocity and time, I can get acceleration. I can calculate acceleration because there is acceleration is change velocity over time. So it's just by using these equations over and over and over, you'll get really good at them and identifying what we need. So you can see I don't know my A there, so I've gone to calculate, my time is 20 seconds because it wants, let's have a look, A, the resultant force around the empty bus, so D, 190 seconds, but it's first 20 seconds, I believe, and where does it say that? Where have I got that from? So it says uniform, the set of traffic lights, A, resultant force, yeah. So it's just on about this bit by here, from A to B. Actually, so it's the force acting from A to B here is 5,000 newtons. Use a graph. So that happens in so this scale, every little square is 0.4. So this point by here is 20. So that's 20 seconds. That's where I got my time from. My velocity, my final velocity is 25 meters per second there. Okay, because that goes up in ones, I think. And then my initial velocity is 0. So when I plump that into the equation, it's going to give me 1.2 meters per second squared. And now I can use that to calculate my mass. And that's what I've done there. F equals ma. Okay, a formula from the front of the sheet. I've stuck it in a triangle because I need to get my mass. And I'm not very good at rearranging. So I've chucked my F on top because ma are together. And that gives me F over A, and then 5,000 over 1.25 is giving me 4,000 kilograms. And then acceleration, is for the next question, the same resultant force acts on the bus, but it's now full of pupils. Got a bigger mass. Explain how the start of the velocity time graph between A and B would change. Well, the acceleration would be less because you got more mass. So the gradient would be less steep. It would take longer to get to the same velocity. So the line would be less steep. Last question then. State Newton's first law of motion. Well, we need to know these because they always come up. And I'm going to go through the 3. So it's first, an object will remain at rest or in a uniform motion in a straight line unless acted upon by an external force. We just need to know that. That just means that if the force is a balance, that object will just remain either at rest or just moving if there's no forces acting on it. So if it's in space, it will just continue on and on. Explain how Newton's first law applies to the part B B to C of the journey. Well, the velocity is constant, so there's no resulting force. The force is a balance there because this just going at the same speed. By the way, I've also thrown his second law, F equals ma. That means that once a force starts acting on an object, it's going to cause it to accelerate. So that's it. So first law, it's not going to do anything if there's no forces. Once a force is acting on it, it's going to cause it to accelerate. F equals ma. And then his third law, if I push down on the table, if I'm body A, exerts a force on body B, and the table is B, the table exerts the same force that I apply to it. It means that I'm not causing it to accelerate, so it's pushing back with the same force. So I like to think of these laws as the third, then second, then first, because I'm trying to push something. If it starts accelerating, then it's the second law. And then if I let go and it's if it's somewhere like in space and there's no particles, that will just continue on forever in a straight line till another force is acting on it. It's 10 minutes 30, so I'm going to try and wrap this up in one video. During this journey from A to D, how long was the bus moving at velocity greater than 12.5 meters per second? Well, that's easy, because I've just got to go to the graph. And I've got to draw a line. My my green line is at 12 meters per second. And then I just actually calculate then. So what I've done is 170 minus 10. So 170 there. So what I've brought it down, look. Sorry, there. 170 and then 10 seconds from there down. So that's how long it's moving above this line. Yeah, it doesn't want to know anything below. That's why I brought the green lines down. That's that question. This may have to be 2 videos because I want to spend some time on this bit, I think. A lorry travels between the same 2 sets of traffic lights at a constant velocity without stopping. It takes the same time as the school bus. On the graph opposite, draw the motion of a lorry. So what it's saying is the lorry is not actually stopping, whereas this bus is. Stop there and then accelerates, go in, and then it comes back down. It wants to know where the line for the lorry would be. And you can see I've put it there, but I'll show you how I worked it out because it's not stopping. It covers the same distance in the same time. So I need to calculate really the area underneath the bus to get my distance. So that's my first part, and you can see section 1 there. I've gone half times 20 times 25 gives me 250. 20 times 25 I've got from the graph there. Okay, so there's 20. 25. I've halved it because it's a triangle. I would have done the same for section C to D. I'd said half times and then half times base times height. And then I wouldn't have halved this because this is all the area. So it would have been base times height, and I'll show you. And you can check these figures. Section 2 is just 150 minus 20, because that is that section there. So it's 150 minus the initial 20 there. So this section. And then I've just 130 times 25 there. That's going to give me 3,200. Oh, I didn't want to do that. 3,250. Sorry, my mind's elsewhere. And then I've got section 3, which is half times base times height there. And all these figures I've got from the graph. And then I come out with an overall distance, when I add them all up, of 4,000 meters. Now, I need to see what my speed would be for the lorry. So I know my distance. I know my time, because it says there it's exactly the same time. So if I know my distance and I know my time, I can get my speed by going speed equals distance over time. And it's really quite easy from there. And that's 5 marks just for something like that. And it was 21 meters per second. And that's why I've drawn the line there at 21 meters per second. Hope that makes sense. Again, if you've got any questions about any of these questions, any of these problems, please come and see me and I'll try and explain better.